Okay, so this week we're going to draw the implications of asymmetric information between investors for portfolio choice. So last week when we studied the model of portfolio choice, we took into account there was some uncertainty, right? So investors did not know what the future payoff of the risky asset would be, but this uncertainty was the same for everyone, right? So in this sense, information was symmetric, okay? Now we're going to take into account the fact that different investors will have different levels of information. So in particular, some will be informed, better informed. Okay, so this week we'll study the implications of asymmetric information for the portfolio choice problem. So far in this course, we took into account the fact that there was some uncertainty, but essentially uncertainty was the same for all investors. But defining features of financial markets that not all investors have the same information. So some will be relatively uninformed, while others will have some privileged information. Okay, so we'll study the consequences of asymmetric information for investment. So for these purposes, we'll consider the following models, and we'll consider three different sets of assumptions regarding the expectations of investors, whether they have rational expectations or not, and then whether there is some additional source of noise or uncertainty on financial markets. Okay, but let's start with the simplest model, and then we'll build on that. Okay, so in this model, so there's two financial assets. So the first one is a risky asset with a payoff which is normally distributed and which is denoted by d tilde. And so the mean of d tilde is d bar and the variance is sigma square. Okay, so also d tilde is a dollar amount. It's not a return. The market price of this asset, so it's a model with 2 dates, right? Time 0 and time 1. So at time 0, the market price of the asset is denoted by P, and the asset is in positive net supply, meaning there's some assets that exist in the economy. The second asset is simply the risk-free asset, which is in perfectly elastic supply and which has a return RF. Okay, so RF is a return, not a payoff. Okay, then we have some investors. So all investors have Cara utility with coefficient of absolute risk aversion, alpha. Okay, and their initial wealth is W0. Okay, so why assume Cara utility? It's simply because we also assumed normal distribution for the uncertainty. And so as we know now, it's going to be quite convenient and quite tractable to be able to get some results in closed form and then to take the analysis one step further. Okay, what about the information? So that's going to be the crucial part. That's going to be very different compared to what we studied last week. So there's two types of investors. There's going to be a number Ni of informed investors and a number Nu of uninformed investors. So what does it mean to be informed? So if you are informed, not only do you know about the distribution of d tilde, but you also receive some additional information. And more specifically, you receive a signal S tilde, which is centered on D. So D is a realization of d tilde, but which is not perfectly informative because the signal is distributed centered on D, but then with some noise epsilon tilde. Okay, so again, yes, D is a realization of d tilde, and epsilon tilde is a random variable, which is also normally distributed with a mean of 0. That's just a normalization to make things simple, and this variance. Okay, so this variance is more important. It tells you to what extent the signal is informative. So of course, if the variance is very low, the signal will be much more informative because it will not be very noisy. But if the variance is very high, it means the signal will not be very informative. And And also, just to make things simple, epsilon tilde is independent from d tilde. Okay, but of course, the signal will still be informative about the realization of the risky assets payoff. So a few things to be careful here. So note that informed investors, they only observe the signal S, right? The realization of the signal S, they're going to observe S equal 2, for example, but they do not observe the realization of D. But obviously, the realization of S will be informative about the realization of D. We will also sometimes need the unconditional distribution of the signal. It is given by this, right? So it's going to take into account the fact that D is a random variable and epsilon tilde is a random variable as well. Okay, so how do these investors trade? Well, each investor can submit multiple limit orders, and so they essentially can submit a demand curve X of P, where X is the quantity demanded of the asset. X can be negative, in which case this is the quantity that they are selling, and P, again, is the asset price. Okay, so they're telling us with this demand curve how much they're willing to buy if X is positive, or to sell if X is negative, as a function of the asset price. Okay, and so each investor is going to submit this demand curve. Okay. Just so what does it mean also for investors to be informed in practice? Well, it can mean several things, right? Here we remain agnostic. It can mean that they have better information, or they have a better ability to make sense of publicly available information. So let's say they have better models to understand existing information. All right, so that's the basic model. So now, how are informed investors going to update their beliefs? And so here we're going to start with some very simple examples, and we're going to look at the formulas that we're going to use. So in this example, so I set some parameter values here for the prior distribution of D. And so here I just assume that the signal observed was S equals to 2. Okay, so here note that the prior expectation for the payoff of the risky asset is that it is equal to 1 in expectation, but you observe a signal which is higher than that. So here S equals 2. So what does this mean? So how are you going to update your beliefs to incorporate this new information? So here I divided this example into 2 parts. So the first one and the second one, depending on the noisiness of the signal. Okay, so in the first figure, so the signal is quite noisy, and in the second figure, the signal is less noisy. So let's start with the first one. So in this case, so everyone has the same prior belief here. So that represents the beliefs of investors regarding the distribution of the risky assets payoff D. And this is the beliefs of uninformed investors, or of anyone who doesn't observe the signal. Okay, this is a prior belief. Now, when you observe the signal, so you do not perfectly know what D is going to be, but you are going to get some more precise beliefs, right? You're going to get a better idea about what the risky assets payoff is going to be. Okay, so in what sense are your beliefs more precise? Well, they're going to be more precise in the sense that the variance, as you can see, of the orange curve here is lower than the variance of the blue curve. Okay, so you have more precise beliefs. Also, you're going to shift your expectation. So under the prior distribution, you expected the payoff of the risky asset to be equal to 1, whereas under the orange distribution, so your posterior belief, once you've observed the signal, now you expect the payoff of the risky asset to be a bit higher. But note that it's not equal to 2, it's less than 2, which is a signal realization, but it's higher than 1, right? So you're shifting your belief, you're becoming more optimistic, but not all the way to the signal realization because the signal is still imperfectly informative. So essentially what's going to happen is that your posterior belief is going to incorporate both your prior belief, but also what you're going to learn from the signal as well. Okay. So now what happens when the signal is more informative? So in the second case, when the variance of epsilon tilde is lower. Okay. Well, so in this case, as you can see, your posterior belief is even more precise, right? The variance of the distribution is even lower. And in addition to that, your posterior belief is going to be much closer to the realization of the signal S equals 2 than to your prior belief, which was equal to 1 for the expectation. Okay. So again, so when the signal is more informative, in a sense of a lower variance of epsilon tilde, two things happen. You have a more precise posterior belief with a lower variance, meaning the residual uncertainty about the risky assets payoff is lower. And also you're going to rely more on the signal compared to your prior belief about the risky assets payoff. Right? Makes sense. The signal becomes more informative. You're going to rely more on the signal. Okay, so now let's look at the actual formula that we're going to use in this setting to update beliefs whenever we receive some new information. So here, these formulas can only be applied for normally distributed random variables. Okay, so that's why we made these assumptions regarding the distributions. And so here I'm going to give you at first the general formula for any two random variables x tilde and y tilde. And then we're going to apply that to the model that we are studying. Okay. So here, so we assume that we are observing one of these two variables that we're going to call x. And now we're studying the effect that this has for our beliefs about y tilde. So y is something we do not observe, but we're going to get some information about y tilde once we observe x. Okay. So this is what is y tilde equal to? Well, so the way we're going to shift our expectations is that the conditional expectation of y conditional on x is going to be equal to the unconditional expectation plus this term, which is going to incorporate how we shift our expectation. So here in parentheses is what I call the surprise, okay, for the variable that we observe, which is x in this case. So we expected x to take this value, the expectation of x, but the realization of x is this. So for example, in the example that we just studied, x was equal to 2, whereas the expectation of x was equal to 1. So there was a positive surprise. So this term was positive. Now the question is, using this surprise, so how much are you going to update your beliefs? How much are you going to shift your expectations? And this is given to us by this fraction here. And this fraction, so what is it? So we call that the beta, as you can see right there, because this is simply the slope coefficient in an OLS regression of y on x. Okay, so the slope coefficient tells us by how much the predicted value of y is going to be sensitive to the realization of x in a linear regression. Okay, so it's the same thing. So for example, if the covariance is higher, it means that these variables covary more, so your posterior belief is going to be more sensitive to the surprise here. Okay, and also this fraction here can be positive or negative. So here, if this is positive, it means the covariance is positive. It means that x and y are positively related. And so in this case, when you observe a high value for x, so when the surprise here is positive, you're going to positively update your expectation for y. And conversely, if this fraction here is negative, it means that you're going to negatively update your expectation for y whenever the surprise here is positive. Okay, so let's apply this formula. So now y is going to be d tilde and x is going to be s. So we observe s, the signal s, and we want to get the implications for the expected value of d tilde, the risky assets payoff. So in this case, so at first we're just going to substitute in the general formula here. So if we do that, so here I'm not doing any calculations, I'm just substituting, I get this equation. Okay. So now we're going to use the model setup and the assumption that we made regarding these two variables to replace in this formula. Okay, so we go step by step. All right, it's important to go slowly to not make any mistake. So the expectation of d, so by definition it's d bar, and the unconditional expectation. What is the covariance between d, the risky assets payoff, and the signal? So here it is given to you here. And when calculating all these variance terms and covariance terms, it is important to rely on the unconditional distribution of the signal. Okay, so we're going to use this. And the second thing which is important is that whenever you have something that looks like this, you're going to substitute for the expression for the signal, or maybe the stock price, if it's a covariance between D and P. Okay, so if we substitute for the signal, so S tilde, which is equal to that, so we're going to replace in this equation. So here I just replaced. And now we have to calculate this covariance term. So what is it equal to? Well, it's going to be equal to the covariance between D and D plus the covariance between D and epsilon tilde. But by assumption, D and epsilon tilde are independent, meaning that we are only left with the covariance between D and D, which is also the variance of D, which is also equal to sigma squared by assumption. Okay. All right, so same thing for the term in the denominator here, the variance of the signal. So again, we use the unconditional distribution of the signal. So we just replace, and so we go step by step to not make any mistake. So the unconditional distribution of the signal, so the signal is equal to this. So normally when you take the variance of a sum, you're going to get some covariance terms. But here we simply use the fact that the covariance between D and epsilon tilde is equal to 0. And so then the variance of the sum is equal to the sum of the variances. So it's equal to this, which is also equal to that in the denominator. Okay. And finally, we have the surprise term. Okay, so S here is the realization of S. It's just S minus so the expectation of S, but in this case, the expectation of S is simply equal to the expectation of D, and the expectation of D is also equal to D bar. So why is that? You can take the expectation of S here on this formula. You take the expectation on the left side and on the right side. The expectation of D is equal to D bar, whereas the expectation of epsilon is equal to 0. Okay. Okay, so the expectation of S is equal to D bar. Okay, so that's it, right? So in this formula, we only have model parameters and the realization of the signal S. So that's as far as we can go. Okay, so now how do we update the variance? So again, the general formula with two normally distributed variables X and Y is is here, okay? And so what is going to be the conditional variance of y once you observe x? So it's going to be equal to the unconditional variance of y. So this is the first term on the right-hand side here, minus something. And here you'll notice that this second term here, including the minus sign, is always negative, right? Meaning that the conditional variance of a random variable is always going to be lower than the unconditional variance. And why is that? Well, simply because you're always going to learn something. Even if the signal is perfectly uninformative, at worst you are not learning anything. Okay, but the uncertainty is never going to get worse. It's always going to get better, if only in a weak sense. Okay, so the conditional variance is always going to be lower than the unconditional variance. And how much lower? Well, again, it depends on the relation between these two variables. Is these two variables, x and y, are very closely correlated? Then the uncertainty, once you observe x, the uncertainty for y, so the residual uncertainty for y, is going to be much lower. Okay, so let's apply this to the problem we have here. So the conditional variance of D, conditional on S. So once you observe S, how much more precisely are you going to know the risky assets payoff? So again, so at first we're just going to replace, right? So y becomes D. And then I'm going to use this notation regarding the beta, right? And simply this is going to be equal to this. We already calculated beta here in this step. Okay. Variance of S, we already calculated that, right? So try to do it at home. And if you just replace, you're going to find that the conditional variance of D, conditional on S, is equal to this. Okay, so to try to understand these formulas, it's useful to just study some spatial cases. So first special case is what happens when there is no uncertainty about the risky assets payoff to start. Okay, so sigma is equal to 0. It means that the asset payoff d tilde is distributed with a variance of 0, meaning that it's always equal to the same thing. Then this thing is, of course, going to be equal to the unconditional mean of d bar. Okay. And so in this case, so yes, d is equal to d bar. What does that imply? Well, so if you use the formulas from the previous slides, it means that there's no belief updating when you observe the signal because there's no uncertainty to start. Okay. You already fully know the risky assets payoff, so there's nothing more to learn by observing the signal. Okay. So the expectation of D conditional on S is still going to be equal to the unconditional expectation of D. And the residual variance of D conditional on S is going to be equal to the unconditional variance of D, which is equal to 0. Okay. Second case. Now, what happens if sigma epsilon is equal to 0? So what is sigma epsilon? This is the variance of this noise term here. So if the variance is 0, it means that epsilon here is always equal to 0. And in turn, this means that the signal is always equal to D. So when you observe the signal, it's equivalent to observing D, the realization of the risky assets payoff. Okay. So once again, there's no uncertainty because now this time the signal is perfectly informative. So your conditional expectation of D once you've observed the signal is simply equal to the signal, right? You put all the weight on the signal. And the residual uncertainty on D once you've observed the signal, which is a conditional variance, is equal to 0. So there's no residual uncertainty. Once you've observed the signal, you know D. So the conditional variance is equal to 0. Okay, third case. Now what happens if the prior distribution of D has an infinite variance? So you have an improper prior. So in this case, the uninformed investors really do not know anything. They're completely in the dark. Okay, so in this case, what happens? Well, in this case, if the prior distribution is completely uninformative, then the only informative thing in this model is the signal. Okay, so in this case, the expectation of D conditional on S is simply going to be equal to the signal realization. And because the signal realization here is still informative, even though D has an improper prior. And so for the same reason, your conditional variance of D conditional on the signal is simply going to be equal to the variance of the signal. Because again, here, the uncertainty is only going to be related to the signal's uncertainty. Now what happens if the signal is completely uninformative? So sigma epsilon is infinite. So here it means the signal does not convey any information, right? So in this case, the conditional expectation is going to be equal to the unconditional expectation, right? You do not update your beliefs once you observe the signal because the signal is completely uninformative. And likewise, the conditional variance is going to be equal to the unconditional variance because, again, you do not learn anything by observing the signal. Okay, so now we're going to use all these tools to analyze the models that we've described right here. Okay, and we are going to start with the simplest possible case where uninformed investors are being naive, meaning that they are uninformed, but they do not draw inferences. They do not have rational expectations. And we're going to understand in what sense. Okay, so in this model, we have a Cara-normal setting, meaning that we'll be able to use a certainty equivalent approach to obtain some closed form solution for the demand of various investors. So that's very convenient. So let's start with uninformed investors. So these uninformed investors only know about the prior distribution of D tilde. They don't have any other information. And so their optimization problem is simply to choose a quantity XU of risky assets to maximize the following objective function. And as we've postulated, we let this quantity XU depend on the asset price, meaning that it submits a demand curve, a demand which is a function of the price. Okay, so they maximize their expected utility of their end of period wealth. So their end of period wealth is equal to this. So they are investing this amount in the risk-free asset, their initial wealth minus the amount they're investing in the risky asset, quantity demanded times the price. And that's going to grow at the risk-free rate. Okay. So the second component of their wealth is their risky asset line. So that's going to be equal to the quantity of risky asset they have multiplied by the payoff of the risky asset, which is, from their perspective, of course, uncertain. So here this is a Cara-normal framework, so we can use a certainty equivalent approach, and we can rewrite the certainty equivalent of uninformed investors like this. Okay, so the first component is simply the expectation of their final wealth as a function of the quantity XU of the risky asset they are going to demand. So you just take the expectation of this. And the second component of the certainty equivalent is equal to minus alpha over 2 times the variance of their final wealth as a function of the quantity XU of the risky asset that they demand. Okay, so we know that the optimal quantity XU demanded is given by the first order condition to this optimization problem, given that the second order condition is satisfied. And so we differentiate this with respect to XU. We rearrange and we find that XU is equal to this. So try to actually do it at home and make sure you find that, right? So as you can see, XU, the quantity of the risky asset demanded will be increasing in the expected payoff of the risky asset, and it will be decreasing in the expected price, in the price of the risky asset. And something which is more expensive is going to be less in demand. And final thing is that demand is going to be lower in absolute value if risk aversion alpha is higher, or if the risk of the risky asset, here from the perspective of uninformed investor, it's equal to the unconditional variance of the risky asset payoff, so sigma square is higher. Okay. Also, with scalar utility, we can observe that the demand for the risky asset is independent of initial wealth, right? Initial wealth here does not show up in the demand there. Okay, so here, essentially, uninformed investors only use the price of the risky asset for their budget constraints. They don't draw any inferences, and they do not update their beliefs based on the price of the risky asset. Okay, so now let's look at informed investors. Their problem is very similar. Now, of course, the quantity demanded is going to be xi, just because they're informed. So just to keep track of that, we denote that by xi. But so the only difference really in their optimization problem is that the expectation is now conditional upon their information, so conditional upon the signal S that they are going to observe. For uninformed investors, here we had an unconditional expectation. So otherwise, everything is the same. But that's an important difference, right? Because now the certainty equivalent is going to look like this. And so here you can see we have the conditional expectation of D, so conditional on S. And here we have the conditional variance of D once you've observed S. Okay, so that's the only difference. So if you take the first order condition, so now xi is going to be given by that. So what are the differences? Well, of course, there's going to be some belief updating for informed investors. So for example, if S is pretty high, the updated belief about the expectation of D, the payoff of the risky asset, is going to be larger than the unconditional belief. It's going to be larger than D bar. The second thing is that regardless of the realization of S, this conditional variance here, which is a measure of the residual uncertainty faced by informed investors, is lower than the uncertainty faced by uninformed investors. So that means that because they are less exposed to risk, informed investors are going to demand more in absolute value of the risky asset. So either they're going to buy more or they're going to sell more because they are less exposed to risk, precisely because they have more information about what the risky asset is really worth. Okay. And that is the case for uninformed investors. The demand of informed investors is going to be less when the price is higher, okay, for the same reason. Okay, so these are for the demand functions of both type of investors. Okay, so now what about the price P? So obviously this is going to be determined endogenously, and it's obtained by market clearing. So market clearing simply means that the sum of demand of all investors on the left-hand side here must be equal to the supply of the risky asset. And here the supply is capital S. And if we go back to the model description, the risky asset is in supply capital S. Okay. So here you have all the demand from uninformed investors, and here you have all the demand from informed investors. So the quantity NU of uninformed investors and a number NI of informed investors. So how do we solve this for the price? Well, it's pretty straightforward, right? So you take both demands, you replace in this equation. Now, likewise for XU, you get XU from the previous slide here. And so here, so for Xi, you're going to have this conditional expectation and this conditional variance. Where do you get that from? Well, you get that from what we did earlier, right? So the conditional expectation will be this, and the conditional variance will be that. Okay, so you just replace. You just replace here, and then you plug that into the market clearing equation. And finally, you just solve for the price. So you isolate the price. And if you do that, you should be able to find that the price can be decomposed into 3 additive components. The first one being the discounted value of the expected payoff, D. So that would be D bar discounted at the risk-free rate. Then it's going to be the price reaction to the signal. So if the signal is higher, the price is going to also be higher, simply because this will drive up the beliefs of informed investors, who are then going to demand more of the risky asset. So you'll need to have a higher price for market clearing. And the last thing that is going to be a risk premium, simply due to the fact that the asset is in positive supply. So in equilibrium, investors will hold a positive quantity of the asset. And because they are risk averse, they need to be compensated for risk. That will take the form of a lower price, a lower asset price. Okay, so you can actually try to do that starting from the market clearing equation, and you can find the solution. So what you should find in the exercises file. Okay, so if we do this, we're going to find that there is not only monotonic, but also a linear relation between the signal realization, S, and the asset price, P. Okay, so that makes sense, right? The higher the signals, the higher the asset price. But what's more interesting is that this means that because there's a one-to-one mapping between the signal and the price, it means that when you observe the asset price, let's say the asset price is here, you can then infer that the signal was there. Okay, so observing the asset price means that in this model, it's the same thing as observing the signal. But then if your demand can be continued upon the asset price, you should be able to actually trade as if you were observing the signal. Okay, so that's a bit of a problem, right? Because in this model, the price fully reveals the signal of informed investors, and yet uninformed investors do not use this information. They observe the asset price, but they don't draw any inferences for what it means with regards to the value of the signal. If they observe a higher price, they're simply going to say, oh, okay, so the asset price is very high, so I'm going to demand less of it. They're not going to draw the implication that perhaps the price is high simply because the asset price is worth a lot because the signal was very positive. Okay, they're not taking that into consideration, uninformed investors. Okay, so in a sense, they are being naive, and the next step will be to incorporate rational expectations. Okay, so what happens when uninformed investors remain uninformed, but now they have rational expectations, they understand how the model works, and they draw inferences when they observe the asset price. Okay, so now let's move on to the rational expectations equilibrium. Okay, so in the naive equilibrium, investors only rely on their private information, and they only know the prior distribution of D. Now, in the rational expectations equilibrium, they're going to learn from market prices, and they're going to take into account the information conveyed by the asset price. Okay, so when we to a rational expectations equilibrium, the reasoning is a bit circular in the sense that we need to know what the market price is going to look like to understand how uninformed investors are going to form their expectations. But in terms, of course, the asset price is going to depend on the demand of investors. Okay, so it's a bit of a circular reasoning. So how do we solve for such a model? Well, the idea is that we're going to postulate a functional form for the asset price. So here we're going to postulate that it is a linear function of the signal. And then we're going to be able to solve for the investor's demand, plug that back into the market clearing equation, and then get the market price. Okay. Here we're going to take a shortcut. We're going to simply assume that the asset price is going to take this form. This could be formally shown, but here we're going to just assume this. Okay, and then we're going to show that the demand of informed and uninformed investors is going to look like this. Okay. So for the informed investors, really nothing changes. So for them, the signal is a sufficient statistic. They do not learn anything else from observing the market price. Okay. So their optimization problem is the same as before. It's the same as in the naive equilibrium. And they are going to have this demand. Now it's a bit more interesting and more complicated in the case of uninformed investors. Okay, because now, so for informed investors, informed investors would condition their demand upon their information, which is the signal. Uninformed investors are going to condition their demand upon their information, which is not the signal, but the market price, P. Okay, and this is why you see that they condition on P here and mostly there in their objective function. Okay, so they maximize the following. It's still the expected utility of their final wealth, which is the same. But now, of course, the difference is that they condition upon P, which is their information. Okay. So as before, if we take the certainty equivalent approach, we're going to get this. Again, this is very similar to what we derived before. The only difference is that the expectation is conditional on P and not S, and the conditional variance conditional on P, not S. Okay, so these are the two terms we need to focus on: conditional expectation and conditional variance. So let's go to the next slide where we calculate the value of these two terms. So let's start with the conditional expectation. So we're going to start with a very standard formula. So here I did not make any calculation. I just substituted in the formula we got at the beginning of this slide deck. And now we substitute using the model parameters and model assumptions. Okay, so the unconditional expectation of D is D bar. This term here is what we refer to as the beta. So here the beta is defined by this formula. And this term here, so this is just a surprise when you observe the price P and you expected the price to be equal to this. And here we're going to denote the expectation of P of the price by P bar. Actually, if we go on the previous slide, using this functional form for the price, now the function of the signal S, if we take the expectation on both sides of this equation, we take the expectation of this, what's going to happen is that you're going to have the only random variable here is S. So you're going to take the expectation of S minus D bar, which these two terms are going to be equal. So this whole thing is going to be equal to 0. And you're only going to be left with the first term and the third term. And this is what you have here. Okay. So P bar is the expected price. So now the trickier term is this one, the beta. Okay, so once again, we just write it down. So it's the same as this by definition. And now we replace. Okay, so before we used to have the signal here, now we have the price. So we simply replace by what we have for the price formula, which is this. In this formula, the first and third terms are constants. So in a covariance, they will not matter. The only term that will matter in a covariance is this one. Okay. So we keep this term in mind and we plug it there. Okay, so here I replace the price by the expression for the price, except that I only insert the term which is not a constant. Okay, so same thing in the denominator. For the variance, I can discard the terms which are constant in the price formula, and I only keep this term. Okay, and as before, we always use the unconditional formula. So, all right, so what do we have here? Now let's try to rewrite this. So this beta over 1 plus RF, that's a constant. Okay, so we can throw that out of the covariance. That's what I do here. Likewise, same term, that's a constant. We can throw that out of the variance, of course. It is now squared. And we are left between, we are left with this term. But what is this? This term is simply beta ds. The term we studied before. Where do we have it? Beta ds. It's exactly this. We already calculated it, and it is equal to that. Okay, so it's beta ds. This is beta ds. But look at that. It's pretty nice now because we have 2 beta ds in the numerator, and we also have 2, and because of the square here, in the denominator. All right, so they're going to cancel out. Now we have 1 plus RF here and 1 plus RF squared there. So the only thing that's going to be left is simply 1 plus RF. So beta PD, which is here, simply going to be 1 plus RF. Okay. So now if we plug this with beta PD equal 1 plus RF in the expression there, you can do the math. You're going to find that the numerator is simply equal to that. Okay, so now let's move on to the denominator with the conditional variance. And here I'm claiming that the conditional variance, conditional on the price, is equal to the variance conditional on the signal. Meaning that the residual uncertainty from the perspective of uninformed investors is going to be the same as the residual uncertainty from the perspective of informed investors. Meaning essentially, both sets of investors have the same information. Okay, so let's prove this result. So again, we start from the very general formula. And then we replace by what we know based on the model. So the variance of D is sigma squared and conditional variance. Here we have beta PD, which is the same thing as what we have here, same thing as what we have there. And we know that this is equal to 1 plus RF. So that's going to make our life easier. And also we have the variance of P. What is the variance of P? We already calculated that there. The variance of P is equal to this. And also it's equal to that, right? And this is what I have there. Okay. So now I'm going to substitute. I'm going to use the fact that beta PD is equal to 1 plus RF to replace here. So that's going to give me my 1 plus RF squared, but I have 1 plus RF squared in the denominator. So that's what I have there. And then I'm going to get the beta ds, which we've already studied, beta ds squared. That's going to be equal to this. And finally, the variance of S. Variance of S is simply equal to the variance of D plus the variance of epsilon squared, because the covariance term is equal to 0. Okay, so some terms simplify, of course. This is going to, this fraction is equal to 1. Here, this is going to partially cancel out with that. And in the end, if you do the math, of course, you have to calculate the unconditional variance minus this whole term. But if you do the math, you'll find that it's equal to this. So look closely at this expression. If we go back a few slides, now this is exactly the same thing as the variance of D conditional on S. Same thing. Okay. All right. Same thing. Okay, so we've established this. So now I can just replace the variance of D conditional on P by the variance of D conditional on S. All right, so we got this for the optimal demand of uninformed investors. Now there's one last step. How do we go from this to that? I can try to think about it. And the idea is simply to use this expression for P bar. Okay, so if you replace P bar here by this expression and you rearrange, you'll find that the demand of uninformed investors is going to be equal to that. All right, so that's a bit surprising. So what does this mean? Let's use again the market clearing equation. And so if we combine equation 1 with the market clearing equation, which is here, total demand for the asset is equal to the supply of the asset, we're going to find that the quantity of the asset purchased by informed investors is going to be the same. Is also going to be equal to S over N, where N is the total number of investors in the economy. Okay. So in this model with rational expectations, so what's happening is that the portfolio of uninformed investors is always going to be the same as the portfolio of informed investors. Uninformed investors are always going to demand the same amount of the risky asset. And why is that? Well, essentially in this model, the uninformed investors will observe the price because there is a one-to-one relation between the signal realization S and the price P. By observing the price, you can do just as well as if you observed the signal. Okay, so even though the uninformed investors are initially at an informational disadvantage, in the end, they can do just as well as the informed investors because they're going to get the same portfolio. So their expected utility of wealth is going to be the same. Okay, and so this is a justification for passive investment strategies. So here, as you can see, the uninformed investors are just going to passively hold, in a sense, a market index. Now, their demand is not a function of the price. They're not trying to beat the market. They're trying to do exactly the same as everyone else. And this just means that you purchase the same thing as everyone else. You purchase the stock market index. Okay. And again, this is because the asset price P reveals the information of informed investors. And so uninformed investors want to hold the same portfolio, and they're going to submit market orders, which is they're going to buy a fixed quantity of the asset regardless of the price. So in this model, so how is the asset price set? So the asset price is still set by informed investors. It's going to depend on the signal. But the portfolios are not going to depend on the signal. Everyone's going to do just as well. The uninformed investors' demand is inelastic with respect to the asset price. Why is that? Well, because there's two effects at play. So as in the naive equilibrium model, a higher asset price is simply going to make the asset more expensive, which is going to drive down demand. But at the same time, a higher asset price is also a signal that the asset's value is higher, right? And so these two effects are going to cancel out in such a way that the demand of uninformed investors is not going to be a function of the price. Okay, so in this case, so indexing is optimal. So when you trade against investors who are more informed than you are, the best you can do is to do exactly like everyone else. So you're going to passively buy the stock market index. So it's a passive investment strategy. So informed investors set the price, so the market is still efficient, and the market price of the asset is still incorporating the information of informed investors. And this is true regardless of the relative proportion of informed and uninformed investors. Okay. So everything's great in this model, right? Markets are perfectly informationally efficient. They transmit information through market prices, and everyone is doing just as well. But now that raises a paradox, right? Because if uninformed investors can do just as well as informed investors, why would anyone ever become informed, right? It's often a bit costly to be an informed investor. You have to gather information. You might have to pay for information. You have to analyze the information. So that's all pretty expensive. So why would anyone do that? No? So that's the limitation of the rational expectations equilibrium. Of course, the lesson that it brings to us is it provides a very strong justification for passive investment strategies. And as you can see, for example, even in the last decade, there's more and more funds which are managed passively as opposed by actively. Okay, but to overcome this limitation of the rational expectations equilibrium, we are now going to study noisy rational expectations equilibrium, which is a model of Grossman and Stiglitz. Okay, so the third and final model we're going to study this week is the model by Grossman and Stiglitz. And it's designed to overcome some limitations of the model with rational expectations. For example, in the model with rational expectations, there was no trade in financial markets. Everyone has the same portfolio. The price is perfectly informationally efficient, and uninformed investors free ride on price discovery. Okay, but the problem, of course, is that if everyone is going to free ride on price discovery, why would the price be informative in the first place, right? So why would anyone be informed? And so the answer provided by Grossman and Stiglitz in this very famous model was that market prices in practice do not exclusively reflect relevant information. They're also affected. The market prices are also affected by a multitude of shocks that are not relevant to the asset's value. But then if that is the case, if the market price is also affected by irrelevant market shocks, for example, shocks due to demand from liquidity traders and so on, if that is the case, then inferences based on the market price will be limited. You're going to learn something by observing the market price, but you're not going to learn everything. You're not going to become as informed as an actual informed trader who has some fundamental information about the value of the asset. Okay, so we're going to make the model more realistic by incorporating this dimension into the analysis and then drawing. So what would be the implications of doing that? Okay, so let's go. So how can we introduce some additional source of noise in such a way that the only random variable relevant in the model is not the signals, it would be also some other source of shock into the model. Okay, there's several ways of doing that. Here's the simplest way, that we're going to assume a random supply of the risky asset. This can also be interpreted, and the model will work exactly the same way if you interpret this as a random demand for the risky asset. Also think about liquidity traders or noise traders who have some random demand for the risky asset. So think about some traders who do not trade based on their information, but simply because, for example, they have some liquidity needs. They need to sell the asset or to buy the asset based on liquidity flows. Okay. And so now, under the random supply interpretation, so now the supply of the risky asset will not be fixed and equal to S. It's now going to be random and equal to S plus U tilde. And as all other random variables in the model, U tilde is going to be normally distributed with a mean normalized to 0 and a variance of sigma U squared. Okay. And so now the market clearing equation is still going to be that the sum of demand is going to be equal to the total supply of the risky asset, which is now random because U is a random variable. Okay. So what is an equilibrium? So an equilibrium is going to be described by the price of the risky asset. So the price is going to be a function of both random variables, which is the signal. So some fundamental information about the value of the risky asset. And then another source of noise, which is not fundamental information, which is going to be denoted by U. Okay. So then an equilibrium is a price and a vector of demands. So one demand per trader. So there's n traders, which are going to be a function of the price, such that so uninformed traders are still going to optimize based on observing the price, as in the rational expectations equilibrium. And informed investors are still going to optimize based on observing the signal, just as in the first model we studied today, the naive equilibrium model. Okay. But now, of course, what's going to be different is that the price is going to take a different form, right? Because there's this additional source of noise that's going to matter for price determination, as given by the market clearing equation. Okay, so as in the rational expectations equilibrium, we need to postulate a functional form for the price. And here we're going to postulate that the asset price is linear in the two random variables in this model, which is S and U. Okay, so here you have a linear asset price for three constants, A, B, and C. Okay, so these variables have yet to be determined. Okay. And of course, you can give some interpretation to these variables. So C, for example, is going to measure the effect of noise shocks, U, on the price, P, relative to the effect of information shocks, S. Okay. And B is going to measure the responsiveness of the price to shocks. So for the informed investors, the optimization problem is exactly the same as before. And for the uninformed investors, the optimization problem is going to be very similar to what we did in the rational expectations equilibrium. But now the difference, of course, is that there's a different expression for the asset price. Okay, so we're going to derive the optimal demands. And the last step will be to use the market clearing equation to get the values of A, B, and C that characterize the asset price. Okay, so how do we do this? Okay, so the market clearing equation is again tells you that the sum of demand must be equal to the supply of the asset. And crucially, this market clearing equation must hold in any case, meaning for any realization of the signal S and for any realization of the random variable U, markets must clear. And the price is going to be established in such a way that markets clear in any case. Okay, we also know that the asset price is going to look like this. And again, this is in any case for any realization of S and U. So now, of course, the question is, how are we going to derive the values of A, B, and C? That's three variables from a single market clearing equation. That's not completely obvious. But what's crucial here is that this market clearing equation must hold for any S and any U. Okay. So what we're going to do is that we're going to plug this expression for the asset price into the market clearing equation. So once we've derived the demand of Xi and Xu, and we'll be able to rewrite the market clearing equation in this way. And if you do it, well, it takes a while, but you're going to see that the market clearing equation is going to be linear in S and in U. And so it can be written like this for some constants A, B, and C. Okay. And again, this market clearing equation must hold for any S and any U. So what does this mean? Well, this means that if you change S a little bit, it must still be the case that the left-hand side of this equation is equal to 0. But how can this be the case that the left-hand side remains equal to 0 if S changes? The only way it can be the case is if B is equal to 0. Little b here, okay? Likewise, the left-hand side of this equation must be equal to 0 for any realization of U. So how can this be the case if U changes a bit? Well, the only way it works is if little c is equal to 0, okay? And now if B and C are equal to 0, how can this equation be equal to 0? That's only going to be possible if A is equal to 0, okay? So actually, from this market clearing equation, because it must hold for any S and any U, we are able to derive 3 equations. So here A, B, and C, so each term contains many parameters. And so we have 3 equations, and that's going to enable us to derive the value of these 3 variables. So big A, big B, and big C. Okay. Here I'm not going through all the math, but they are in the exercises file. So you'll see in more details how to do this. Here I'm just giving you an overview of the method used to derive the values of these 3 variables. Okay. All right. So what does this mean? And how does the Grossman-Stiglitz model compare to the rational expectations model? Well, in the rational expectations model, essentially we had this relation, right? It was a model with U being equal to 0 in any case. And then if you observe the signal, so if you observe the asset price, you knew what it meant in terms of the signal realization. Okay. In the Grossman-Stiglitz model, it's a bit different. You're still going to learn from the asset price, right? It's going to be informative about what the signal was, but it's not going to be perfectly informative now, okay? So for example, if you observe an asset price of 0.5 here, you are going to update your beliefs regarding what the signal was, but you're not going to perfectly know what the signal is, okay? And so instead, you're going to have a probability distribution over the signal realization, okay, which is depicted here in orange. So you can actually do the math. You can calculate, so what is the expected signal given the asset price? So we use a standard formula. And if we replace, so again, here we're going to use the postulated form for the asset price, which is here. And we plug that into this, this formula, and we replace. So this fraction here is going to become something like that. Here's the expected price. It's simply going to be equal to the constant A, because the expectation of U is 0 and the expectation of S is D bar. Okay. And likewise, we can calculate the conditional variance of the signal, so conditional on the price. And as you can see, actually, this is independent of the signal realization, of the price realization, and it is equal to this. Okay. So there's going to be some learning for uninformed investors, but it's going to be imperfect learning. The price is not going to fully reveal the information of informed investors. And as a result, even though they learn a bit from the price, uninformed investors are still going to be at an information disadvantage. Okay. And because they don't have the same information, they're going to have a lower expected utility. Okay. So here, so if you do the math in this model, again, it can take a while. I'm not going to go through all the steps here. But if you calculate the expected utility of informed investors and you compare it to the expected utility of uninformed investors, you're going to see that it's equal to this ratio and that it is less than 1. Okay, so the relation still goes in the right direction because here so here both terms are negative, right? So if you throw one term on the other side, that changes the sign of the inequality. Okay. And so as you can see here, so what is going to introduce a divergence between the expected utility of informed and uninformed investors? Well, it's going to be the fact that the residual uncertainty on the value of the risky asset given the signal is going to be less than the residual uncertainty on the value of the risky asset conditional on the price. In other words, the signal is more informative than the asset price. And because informed investors observe the signal, they are going to be more informed than uninformed investors who just observe the price. Okay. Of course, in the rational expectation equilibrium, this fraction here was just equal to 1. And so each type of investors was just as well off. Okay, but that's not the case anymore here. And it's precisely because now the price does not fully reveal the signal. It does not fully reveal the information of informed investors. So in the Grossman-Stiglitz models, so becoming informed as a cost. Okay, and so the cost of information is C. You can become informed, and so you observe the signal S if you pay this cost C. And so how is the proportion or the number of informed and uninformed investors determined? It's going to be determined by an indifference condition, by the fact that your expected utility, all things considered, so your information and the cost of acquiring this information, your expected utility must be the same whether you are informed or uninformed. Okay, so this is what this equation is telling you. All right. So what are the implications of this? Well, what we're going to do is that we're going to rewrite the numerator of this equation, of this fraction. And what is it equal to? Well, if we just omit the minus sign here, it's going to be equal to this. But then we have the exponential of a sum, which, as we know, is equal to the product of the exponentials. Okay. So we can rewrite this like that. Now we have the expectation of a product of two terms. But here, if you look at this one, this is just a constant. Okay, this is the exponential of alpha, which is a constant, the risk aversion, and C, which is just the cost of information. Okay, so I can just take that out of the expectation operator. And so it's just right here. Okay. So if I use that and if I replace this expression here by this, and I rearrange this equation, I simply get that equation. Okay. But now if I combine that equation with what I got on the previous slide, which was this, I get this result. Okay, and this is giving you essentially the relative informativeness of the price compared to the signal, and it's going to relate this to the cost of becoming an informed investor in such a way that this indifference condition is satisfied, in such a way that investors are indifferent between being informed or being uninformed. Okay. So if we are interested in the level of price informativeness, so price informativeness can be measured by this, this fraction right here. So why is that? Here in the denominator, you have the residual uncertainty on the payoff of the risky asset once you observe the price. So for example, if this residual uncertainty is 0, here you have a price informativeness which is infinite. Now the price fully reflects the value of the risky asset. On the other hand, if this residual uncertainty, so if sigma is very high, this fraction is going to be very low, so you have a very low price informativeness. Okay, so the left-hand side here is a measure of price informativeness, how informationally efficient asset prices are. But so using this equation here, we can write the price informativeness. We can decompose it into these two components on the right-hand side of this equation. Let's start with the second one. So here, this is an upper bound for the informativeness of the stock price. And this is saying that the stock price can only be as efficient in informational terms as the signal is. So at most, the asset price is going to reflect the information contained in the signal. But of course, in this model, the asset price is not going to fully reflect the information contained by the signal. This is what we have here. And so why is that? Well, so in mathematical terms, it's because of this term, right? So here, these two things are positive. So here we have the exponential of something which is negative, which is going to be less than 1, okay? So the asset price is going to be less efficient than this. It's not going to reflect all the information contained by the signal. And this is going to be all the more pronounced. So the divergence between the information contained by the price and by the signal is going to be all the greater that C is higher, that the cost of information is higher. And so why is that? Well, it's because of this equation, right? If the cost to becoming informed is going to be higher, then there needs to be an even greater discrepancy between the information contained in the price and the information contained in the signal for investors to still be indifferent between being informed or being uninformed. Okay? Or in other words, if it's very costly to be informed, it must be the case that it pays a lot to be informed, in the sense that observing the signal has a lot of value compared to merely observing the price. So in other words, the price must not be very informative compared to the signal. Okay. So there's a very important lesson from this model. It's that the price cannot be perfectly informative. Markets cannot be perfectly efficient, right? Because if it were, then no one would be willing to become informed. No one would be willing to pay the information costs. Okay. And so it must be the case that informed investors are at an advantage, and so they are willing to pay to be at this advantage. They're willing to pay the information cost. So the first lesson from this model. The second lesson is that now we understand a bit more. So what are the drivers of stock market efficiency? Okay, in particular, as the cost of information decreases, markets are expected to become more efficient. Okay. And finally, so in this model, so we can explain that there's a coexistence of informed investors and uninformed investors. It's not that some investors are irrational. It's just that they're making optimal decisions in such a way that investors will be indifferent between being informed or uninformed in equilibrium. And in this model, there's not going to be too many informed investors, because if there were too many informed investors, because each informed investor is going to trade on his information, that would push the price towards the signal. So markets would become more efficient. But if markets become really too efficient, so if this term here becomes very close to this one, then informed investors are not compensated for the cost of information anymore. Okay. So there will be an equilibrium number of informed investors that cannot be too low, that cannot be too high either. Just so that this expression here is going to be satisfied. Okay, and so markets are not perfectly efficient. They are as efficient as they can be, given the fact that it is costly to become informed. Okay, so how can you work on this? So there's a few exercises in the exercises file, as you can see. So question A, question B, question C, each of them on one of the components of the model that we studied today. So try to look at it and try to do the exercises. All right, that's all for me.